Hello and welcome to lecture number 6 in the course Advanced Robotics Applications. In the last class, I discussed about DH parameters, how do we make the DH parameter table, and then from the table, how do we make the various transformation matrices. And once we multiply all the transformation matrices, we get the relation between the end effector position orientation, that is the last frame, with respect to the base frame or the zero frame. Okay. So today we'll proceed from there. Now, before we proceed, we'll also have to look at inverse kinematics and forward kinematics of industrial robots. Now, the examples that I showed in the last class were very simple in the sense that they are good for understanding. They had 3 degrees of freedom systems only, and they consisted of revolute and prismatic joints. But industrial robots would have a larger number of degrees of freedom. For example, the Puma robot would have 6 degrees of freedom, okay, 6 revolute joints. So today, first we'll start off by very quickly revising the DH parameters of a Puma robot, and then we will move on to the forward kinematics and inverse kinematics. Again, we'll start off with simple examples, and then we'll move to more complex industrial robotic systems. Okay, so today we'll first revise a little bit about our inverse kinematics, not inverse kinematics, our DH parameter assignment for a real industrial robot, and then we'll move on to the forward kinematics to be followed by inverse kinematics. Now, very quickly revising what we were doing in the last couple of classes, that is, we were assigning the axis notations based on the DH convention. And that basically means that if you have a 3 degree of freedom system again like this, very simple, the Z axis is axis of rotations or translations. Okay, that is Z axis. X axis is the shortest distance between the Z axis. Now, in case Z axis are intersecting, then X axis is perpendicular to plane of Z axis of Zs. Okay, so this is the case where the Z axis are intersecting. Okay, now this is the case where they're not intersecting, so it's a pretty straightforward case. So what we can see in the robot on our left, I will assign the Z axis again. Now, I have already revised it once or twice in the last class, but I'll just go through this quickly again so that before we move on to the Puma robot, just to refresh your memory. Now here, Z axis is the axis of rotation, so it is Z0, Z1, then Z2 is here, Z3 is here. So in this particular case, this is a 3 degree of freedom 3R manipulator, okay. This is my X0, that is X1, X2 and X3, okay. And we said that we have to identify the parameters A, alpha, D and theta, and we also said what these parameters are in terms of the DH table. So A is the distance between the Z axis, this is the angle between the Z axis, then D is the distance between the X axis, and this theta is the angle between the X axis, okay. Okay, so let's proceed from here. This is a simple case of a 3R planar manipulator. Now, let's look at a more complex industrial robot. Well, not complex, but an industrial robot having 6 degrees of freedom. Okay. So, we'll discuss about the Puma robot. So, this is the Puma robot, which is called the primary. So, this is called Puma. The name comes from primary universal machine for assembly. Okay, so Puma stands for Primary Universal Machine for Assembly, one of the earliest robots made somewhere around 1960s. Now, it has 6 degrees of freedom. There are 6 degrees of freedom this manipulator has. Okay. Now, the joints, let's look at the degrees of freedom and then try and write the DH parameter table. So, let me write the DH parameter table here, A, alpha, D and theta. Okay, for this robot, there is 1, 2, 3, 4, 5 and 6 degrees of freedom. Now A is the distance between x-axis, this is the angle between x-axis. I've repeated many times, but this is just to make you remember. Sorry, A is the distance between the z-axis, A is the angle between the z-axis, distance between x-axis, and this is the angle between the x-axis. Okay, so now let us assign our axis and try to find out how to make the DH parameter table. Now the first axis, please understand how this Puba-Melpreter moves. The first axis is this one, okay, and this is a rotation. It can rotate this way. So it's a Z0 and a Z1 there. That's my first axis. It is something like, it is also called the waist axis. So it is something like your waist. So if you move your hand, okay, your arm, you're going to move across the waist. So this is like the human waist here. So this is also called the waist axis, and it moves. The waist axis is a vertical axis. Okay. So this is like if you're standing on this side of the robot, I mean on this side, that is your left hand, if you can imagine it that way. And this is your waist here now. And your waist axis is a vertical axis. So Z0, Z1 is marked here. Now Z2 is this axis which is called the shoulder. So this axis is called the shoulder. It's like the arm can go up and the arm can go down. If you can imagine, this is the shoulder axis, and this is my Z2 axis. Okay. Now Z3 axis is this one, which is the elbow. Okay. So this is like your elbow. If you can imagine this to be your left hand, this is your elbow. And at the wrist we have a roll, pitch, and yaw axis. Okay, these are three motions called the roll, pitch, and the yaw axis. Okay, and now all of them meet at the wrist, which is given here. So this is my roll axis, so it can roll about this axis. Okay, now this part is shown in the next figure more closely. So this was the elbow joint. Okay, this is my wrist joint. So this is called the roll axis. It can roll about the wrist like that. So that's a roll axis. Z4 is there. Now Z5 is a pitch axis, which is on this side. This is on that side, or rather it's on that side. So it is Z5 is there, and then Z6 is again on this side, which is my Z6 axis. Okay, so there is a roll, pitch, and a yaw axis. So three axes are at the wrist. The roll axis, which is this one, that's my roll axis. The pitch axis is this one, that's my pitch axis. Okay, and my yaw axis again is this one back here, which is called the yaw axis. All three of them are orthogonal axis actually. Okay. Now let's look at the structure of the robot. We have marked our Z axis. Now I have to mark the X axis. Now here we see Z0 and Z1 are the same axis. Okay, but Z2 and Z1 are perpendicular to each other, so there is a 90 degree here. So basically we have this like this. So Z2 and Z1 are intersecting, which means that X1 and X2 are going to be perpendicular to the plane containing the Z. So this is the plane containing the Z's. So it will be X1, X0, X1, and X2 are the same axis. Okay, this is similar to the robot we saw in the last class. Now X3 is again coming out like this, the shortest distance between the Z's. Then if we go to our wrist axis now, then what we see is that Z4 and Z5 are intersecting. So this is the plane. Okay, so on that plane, so X4 has to be perpendicular to the plane. So we have the three axes X4, X5, and X6 as the same axis. Okay. Now there are some distances that we have seen. Now let's look at the distances again. Now let's write the DH parameter table when the distances will become clear. So first is Z0 and the 0 frame and the first frame, second frame, third frame, fourth, fifth, and fifth, sixth. Okay. So now if we have a 6-axis system and we have so the first one is the relation between the 0 frame and the first frame, or the first frame and the 0 frame. Now you can see from here that the Z0 and the Z1 are the same frame, are the same axis. So there is no distance between them, it's 0. There is no angle between them, so it is 0. And now what about X is the distance between the X axis. Now X1, X0 are the same axis. And hence this is 0, so this is theta 1 now. Okay. Now what about 2? Z2, the second frame and the first frame. So we see that Z2 and Z1 are intersecting. Okay, if they're intersecting, there cannot be any distance between them, so it is 0. What about the angle between them? So the angle between them is 90, and it is minus 90 because it is a rotation clockwise about the x-axis. So it is a minus 90. What about the distance between the x-axis? So x1 and x2 are the same axis here, so it is shown as 0. There's no distance between them. or they're intersecting at a point. So it is 0 and the variable is a theta 2. Now for the third one, now what we see is, let us look at the third axis. The third axis is here, okay, and the second axis is here, okay. So if the second axis is here, so let me draw it in red color, you'll understand. So how did the origin of second axis become the third axis? It moved like this till here, then it came like that. So there are two distances. One distance is this one, the other distance is that one, okay. So this distance is the distance between the z-axis, okay. So this is an A2, so that's my A2, okay. Whereas this distance is a distance between the x-axis. So x2 and x3 is this distance now, which is my D3, which is here. Now they are parallel axis, so this is 0 and that is theta 3, okay, and this is theta 3 then, okay. Now from the third to the fourth, let's go to the next figure. Okay, let's go to the next figure. So from third to fourth, this is my third, Z3 is that side. Okay, now Z3 and Z4, Z3 is on this side and Z4 is on this side. I hope you have seen, let me rub this off. Z4 is here. Okay, so basically what we are seeing is that there is a distance, there are two distances. One distance is the distance between the origins, that is the distance from here to here. That is the distance between the origins, this distance. So the distance between the x-axis, so x3 is that side and x4 is this side. So the distance between the x-axis is given by d4. And also there is a distance here. So the distance between the z-axis, z4 is, the line of z4 is this line. And z3 is that side. So this distance is there, which is a3. Okay. So the distance between z-axis is a3. So there is an a3 there. What is the angle between the z-axis? Now there is a distance of 90 degrees about there's a 90 degree about the x3 has rotated in which direction? Clockwise, and become z4. So this is going to become a minus 90. Okay. And what is the distance between the x-axis? So if you look here, what is the distance between the x-axis? So x3 is this side, x4 is that side. So distance is d4. Okay. So this is my d4 and that's my theta 4. Okay. Now if I look at the fourth and the fifth axis, let's look at the fourth and the fifth axis. Fourth is here, fifth is that side, that's my z5. So there is an anti-clockwise rotation of 90 degrees and they're intersecting at a point. So there is no distance between the z-axis or the x-axis. All the x's are here and all the z4 and z5, z6 are intersecting at that point. So there is no distance between them. What is changing between them is the angle between them. Okay, so z4 has rotated anti-clockwise by 90 degrees and has become z5. So this is a rotation about, this is 0, 90, this is 0, that's theta 5. Okay. Now what about z5 and z6? Z6 has come back this side again, that's my z6. So that's z6. So z5 has rotated clockwise about the x5 axis and has become z6. So this basically means that this axis is going to become minus 90. It is 0, 0 and theta 6. Okay. So this is the DH parameter table for the Puma manipulator. It has 6 degrees of freedom. And these are the various parameters, the A's and the D's, which are corresponding to this manipulator system. When we go to our kinematics of this, what we'll do is we are going to make, using each of the rows, we are going to make the transformation matrices. And from the transformation matrices, we are going to multiply it out such that I get the position orientation of the end effector. That is this one, the position orientation of the end effector here with respect to the base frame. Okay. So that we'll do when we come a little bit later after we do our forward kinematics and our inverse kinematics. Okay. This is the diagram for the Puma manipulator. Okay. Now these are the various transformation matrices. If I take each row, so this will become T0 to 1, T1 to 2, T2 to 3, T3 to 4, T4 to 5, and T5 to 6. Okay, and I multiply them out, I'll be getting the final matrix T0 to 6. Okay, so I multiply each one of this out, and what I get is the final matrix, which is T0 to 6. Okay, so these are the 4 matrices, 1, 2, 3, 4, another 2 are this side. Okay, so these are the other 2. So when I multiply them out, you get a very big expression, which will be something like this, which will look like this. This is a pretty big expression. So R11, So the final matrix that comes out is R11, R12, R13, R14, and each of these terms is given by this. There are 6 variables, 6 thetas, theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. So you can see that all these thetas come in all various combinations, sine, cos in different combinations. Okay. So yesterday when I was talking that for a real manipulator, it's not very easy to, well, it's time consuming maybe, and there's a high chance of making a mistake when you're writing out the final matrix with reference to the base frame. Okay, so this is what I was meaning, that for a 6 degree of freedom system, there are 6 thetas, and they come in various combinations of sines and causes. So basically what happens is there's a high chance of making a mistake. Okay, anyway, we'll come back to this as we proceed when we talk about the inverse kinematics of the Puma manipulator. Now at the moment, next let us look at what we call the kinematics. Now kinematics is the study of motion. So kinematics is the study of motion without reference to forces. Okay, so if I might just draw this figure here, this block diagram here. So all studies in engineering involve forces and motion. Okay, forces or motion, or forces and motion. So studies where there is no force and no motion, there is no motion here, and motion and force. Okay, so either force is there or force is not there, and here no motion is there and motion is there. Okay, so studies in which there is no force but there is motion, this is called kinematics. Okay, so kinematics is the study of motion without reference to forces. Okay, so if you figure out when we can talk about a 4-bar mechanism which is just moving, we can talk in terms of the angular velocities and the linear velocities, and not talk about the forces which are acting at the joints. Okay, such a study would be called kinematics. Now the other is, if you are looking only at force and you have no motion, so no motion, only forces, this is called statics. Okay, so we are talking of statics. Okay, and if you are having motion and forces, we call this dynamics. Okay, so these are the 3 studies: statics, kinematics, dynamics, and this portion is basically called ergonomics. So ergonomics, styling, etc., where they may not really consider forces and motion. Okay, for example, if you design a car, what will be the color of the car? Now that has nothing to do with the forces and motion of the car. Okay, but it's an important study because it determines the market value and things like that. For example, if you color a car bright pink, then probably nobody's going to buy it. Okay, but such studies do not have anything to do with force or motion and are sometimes called styling, design, ergonomics. Now we are talking in terms of kinematics, and what we'll look at now is kinematics. That is, we'll study the motion of the manipulator without reference to forces. Okay. Now, in the case of a two-link manipulator, two-link again, because we want to make it simple. So I have a two-link manipulator. This is theta 1, and this is my theta 2. Okay, this is my point xy. Okay, this is my link length L1. This is my link length L2. Okay. Now, kinematics can be divided into 2 parts. So kinematics can be divided into 2 parts. One is called the forward kinematics, and the other is called the inverse kinematics. So forward kinematics and inverse kinematics. Okay. Now, what is forward kinematics? Now, if I give the input here as theta 1 and theta 2, okay, theta 1, theta 2, joint angles are, the link lengths are already known, so L1, L2 is already known. Then I need to find out what is x and y. Okay, so now what is x and y? Suppose I draw this would be easier to understand. If this is my x-axis and that's my y-axis, then what is x equal to? X is equal to L1 cos theta 1 cos theta 1 plus L2 cos, let me write it in full. So L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, what about y? Y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, now in this equation there are two equations, there are two unknowns. What are the unknowns here? Theta 1, theta 2, there are two variables rather. So theta 1 and theta 2. So suppose I give you the values of theta 1 and theta 2. Suppose I say L1 and L2 are known from before because the link length is fixed, that cannot change. So L1 is equal to L2 is equal to 1 meter, for example. And theta 1 is 30 degrees and theta 2 is equal to 60 degrees. So can you tell me what is xy? Okay, so that is my forward kinematics. So my input is the joint angles theta 1, theta 2. So I'm giving joint angles theta 1, theta 2. And from these two equations, if I just put in the values, I'll get x and y. So I'm getting x and y here. This is called forward kinematics. In the inverse kinematics, which is more important, is if I give you x and y, okay, suppose I give you x is equal to 1.36 and 1.36. Suppose I say x is this and y is that, xy values. Can you tell me what is the corresponding thetas now? So this is the inverse problem now. Suppose I give you xy as an input to the system. Can you tell me what is theta 1, theta 2? Okay, I hope you understand the difference between forward kinematics and inverse kinematics. So in forward kinematics, I give you the joint variables, numerical values of the joint variables, and I want you to find out what is x and y numerically. Now in inverse kinematics, suppose I give you the joint variables theta, x and y. Now corresponding to x and y, can you find what is theta 1, theta 2? Okay, that is the inverse kinematics problem. So to find out theta 1 and theta 2 from this equation, these two equations, we need to solve these two equations to get theta 1, theta 2. Suppose I give numerical value here, 1.36, 1.36. Now I tell you, can you find theta 1 and theta 2? So this is as good as trying to solve the system of equations and finding out what is theta 1 and theta 2. Okay. Now from the control point of view, let's go back to the control point before I come back here again. So let me go back to the control point before we come back here. So how is the robot actually controlled? Okay. So if I look at TrueLink robot like that, so at the joint, there will be a motor. Okay. There will be an encoder or a position sensor at the back and a gearhead in front. Okay. We'll give voltage to the motor will rotate. So if the motor rotates, okay, there will be an angular velocity here. And this angular velocity will cause a velocity at the end effector now. Okay, so both the theta 1 here and theta 2 there. Okay, so there is another motor which is given there. Okay, this encoder, that's here. Okay, this is also called independent joint control. Now suppose the manipulator is here at some xy. Suppose the manipulator is at some xy position. Okay, now we want to take the manipulator to some other position. I want to take the manipulator here. I want to take it there. Okay, that's a different x dashed, y dashed. Okay, so this is my theta 1 dash now, theta 1 dashed, and that is my theta 2 dash now. Okay, now how does the controller do that? What it will do is at xy, it will do inverse kinematics and find out what is the corresponding joint angles theta 1 and theta 2. Okay, numerically it will find out theta 1 and theta 2, the numerical values. Say for example, this one is let's say 40 degrees and this one is 60 degrees. But on the other side, this one let's say is 80 degrees and this one is 90 degrees now. Numerical values. So now what it will do is from inverse kinematics for this xy, it will say the numerical value is theta 1, there's a joint. Let's say theta 1 is equal to 40 degrees and theta 2 is equal to 60 degrees. How it will know that? From inverse kinematics. Now at x dash, y dash, it will again do inverse kinematics. So it will do IK or inverse kinematics and it will find out the corresponding theta. So theta 1 has become 80 degrees now and theta 2 has become 90 degrees. Okay. So what the controller will do is it will do theta 1 minus theta 1 dashed or theta 1 dashed minus theta 1. Theta 1 dash minus theta 1 and it will get what is 80 minus 40 which is equal to 40 degrees. Okay, so we say this is an error, so del E1 for is equal to this. Okay, that means it is doing this minus that, this minus that. So the controller understands that it has to move by 40 degrees now. Okay, so what will happen is the controller will give a voltage to the motor and the motor will start rotating. If it starts rotating that side, what will happen is this angle will start increasing. So the moment the angle starts increasing, what will happen? This error will start decreasing. So if this del E1 going towards 0, the moment it becomes 0, it basically means that this value has become equal to that value. Okay, so the link will start moving like this. Okay, it will start moving like this. So the moment it has reached, it means theta 1 and theta 1 dashed have become equal. So theta 1 dash minus theta 1 will become 0. And that means it has reached. Similarly, it will do exactly same for this theta, the error 2. So it will do 90 minus 60 and get 30 and then drive to this 30 to 0. Okay, drive it to 0 means it will start increasing this one until the two angles become same. And that's how the controller works. Okay, so it will keep giving voltage to the motor so that the motors will rotate either clockwise or anti-clockwise and make the error to be 0. Okay, now so that is how the controller works, and this is what the and hence inverse kinematics is more important, and hence inverse kinematics is more important because when you're given, whenever you want to go to some point, I want to go to this point x dashed y dashed, the controller has to do inverse kinematics of that point and then find out what is the corresponding theta 1 and theta 2 which will take it there. Okay, and hence inverse kinematics is more important than direct kinematics. Now there is a little catch there in the sense that as you can see in this expression, there is cos and sine terms, cos and sine. Now because of this cos and sine terms, it will always have, it will not, well, not always, it will it may have two solutions. What I mean is cos of cos 0 and cos 180 have the same value, cos 0 and cos 180. Okay, so sine 0 and sine 180 have the same value. Okay, that means these are two solutions. So it means that there would be two solutions. For example, if this is the position there, this will be the other solution which is there. I hope you understand that. X and Y is the same, but theta 1 is this one and theta 1 dashed is there. If this is your theta 2 and this is minus theta 2 now, that means there are two solutions for every xy. Okay, in the inside of the workspace. Once they go to the boundary or they go to a singularity, then you may have only one solution or no solution. Okay, so this basically happens because sine and cos can have two values, and for these two values you will get two pairs of solutions. So for a higher degree of freedom manipulator, you may have more number of solutions. For the Puma 6 degree of freedom arm, you may have 6 solutions. Okay, so this is the forward kinematics and this is the inverse kinematics, and this is what we mean by the basic control. So as we are progressing, I'm trying to make the connection. What we'll be doing in the experiment is you have to decide, when we say design the controller, we have to design how to give a voltage to the motor. How much voltage are you going to give? What is the direction of the motor rotation and how will it reach the desired position? Okay, let's proceed. Now we talked about forward kinematics. Okay, now let's I'll draw this figure again. So this is L1, that's L2. Okay, let me say this is my X0, that's my Y0, just to understand. And this my Z0 comes out this way. I'm not drawing it, that's my Z0. Okay, now this is my angle theta 1, that's my angle theta 2. We can do that using DH parameters. Okay, now if this is my point XY, okay, then from geometry I can write X is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, that's one equation. Now, okay, let me do it this way. So let me add one more degree of freedom here. Okay, so that is theta 2, this is theta 3. Okay, now this is the point XY. Okay, so now we have this is my frame 3 and this is my XY. You can put your DH parameters and then it will come to the same thing. This will become our X3 and this will become our third origin. Okay, so what about Y? Y is equal to, I hope you're following what my how I'm writing these equations. Okay, so this is my x1 is this much and x1 plus x2 is this one, so that is sorry, L1 cos theta 1 is this one, and L2 cos theta 1 plus theta 2 is this one. So my total x, this is my x, right, is equal to this equation. My total y is this equation. So this is y, which is equal to this much plus that much. This much is equal to how much? It is equal to L1 sine theta 1. This is equal to L1 sine theta 1. So sorry, this one is equal to L, this much is equal to L1 sine theta 1, and this one is equal to L2 sine theta 1 plus theta 2 plus L2 sine theta 1 plus theta 2. Okay. Now, what is the total angle that it has rotated? The total angle is phi, which is equal to theta 1 plus theta 2 plus theta 3. So this is the position, and that's the orientation. So these two are the positions of the third frame, and this is the orientation phi. So you have three unknowns, theta 1, theta 2, and theta 3, and you have three equations. Okay, so we have unknowns. How many are the unknowns? Unknowns are three, that is theta 1, theta 2, and theta 3 are unknowns, or the joint variables. And how many equations do we have? And we have three equations. So we should be able to solve. But please note that these equations are not algebraic equations. They are transcendental equations in the form of they have cos and sine, and they have this cos theta 1 plus theta 2, sine theta 1 plus theta 2. That makes it difficult to solve. Okay, so the standard way of solving this is you have one equation here, two equation there, and this is the third one. So what we do, because we observe that there is a cos and a sine, in order to solve it. So in forward kinematics, this is my forward kinematics. Okay, given thetas, find xy. Okay, now for inverse kinematics, I need to solve for theta 1, theta 2, theta 3. Okay, that is my inverse kinematics. I need to find the value of theta 1, theta 2, and theta 3. Now, how do I do that? I can square and add this two equations. Okay, so squaring and adding. Okay, 1 and 2. What we get is x squared plus y squared is equal to L1 squared cos 1 squared, I'm writing in short, plus L2 squared cos 1 2 squared plus twice L1 L2 cos 1 cos 1 2. Okay, this I'm writing in short as cos 1 2, this I'm writing in short as cos 1. Okay, plus the second term I'm writing below, L1 this is L1 sine 1 squared plus L2 sine 1 2 squared plus twice L1 L2 sine 1 sine 1 2. Okay, so I'm squaring and adding both these equations. I want to find out the values of theta 1 and theta 2 and theta 3 for inverse kinematics. Okay, okay, now squaring and adding, we see that if I add, there is a sine 1 squared and a cos 1 squared, sine 1 2 squared plus cos 1 2 squared. Okay, so and here there is a sine 1 2 cos 1 2. Okay, so basically what we can do is I can add this and this, so it will become L1 x squared plus y squared will become equal to sine squared plus cos squared will become 1, so it will become L1 squared sine 1 squared plus cos 1 squared. Okay, plus here this and this, it will become L2 squared just sine 1 2 squared plus cos 1 2 squared. Okay, plus this is twice L1 L2, and what will be inside? Cos 1 2 cos 1 2 plus sine 1 2. Now this term here is equal to cos of theta 1 plus theta 2 minus theta 1. Okay, so this theta 1 will cancel, so it will become cos 2 or cos theta 2. Okay, so now I'm writing on the next page. So next page, the expression that we get is x squared plus y squared is equal to L1 squared plus L2 squared plus twice L1 L2 cos 2. Cos theta 1 is gone. So cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2 Okay. Now what we see is that this is cos 2. Okay. Now we should not take the cos inverse here. Why? Because as I was explaining some time back, there are two solutions or pairs of solutions. This is one solution. This is the other one. So this is one solution. And there is another solution, which is this one. Okay. So if this is theta 1, that's theta 2. This is theta 1 dashed. And this one is minus theta 2. Why? Because cos of minus theta is equal to plus theta. Okay. So cos of theta 2 will become equal to cos of minus theta 2. So the software or the program will not be able to distinguish between these two angles. So it should not happen that you take this angle. So it should not happen that you take this one, theta 1 as one solution, okay, and minus theta 2 as the other solution. So x and y, what I'm trying to say is, if you take theta 1 and you take the other fellow, theta 2, that will actually not match. What will happen is, that your manipulator will become like this. So there is no connection here. Why? Because this is my theta 1 and that one is my minus of theta 2. Okay, because of this problem. So we don't take inverse of cos. So we do not take cos inverse is not taken. But from sine cos 2, we get sine 2. I convert it to sine 2, which is root over 1 minus cos 2 squared. Okay. Now what we take with theta 2 is equal to a tan 2. A tan is a special function which takes positive sine 2 and it takes cos 2 and gives you theta 2. Okay. So this function, which is a special function, in the sense that it takes positive, so it takes positive sine and cos terms. Okay. So this condition will not happen, that it will take one minus and the other one plus. Okay, because the software may not be able to distinguish between this and that, because they are the same value. Okay. So so this a tan 2 function takes both positive sine and cos. So once you use this a tan 2, you'll get the value of theta 2. So now we have got theta 2, we need to get what is theta 1. Okay, so now we can get theta 1, going back again here now, in this equation, there are two equations, right? This one and this one, this one and this one. So in these two equations, if you want to get theta 1, we can use algebraic substitution, okay, or we can use geometry. Let's use geometry because that is easier. You can do the algebraic part also by yourself. So using geometry, it is much easier. So this is one part. This is my x naught. That's my y naught. Okay. So now this is my point xy. Okay, so let's make this very simple substitution. So we take this, I make this very simple construction here. Okay, very simple construction I make. This is my angle theta 2. This is my angle theta 1. I have already found what is theta 2. I need to find theta 1. Now let's assume that this angle is equal to, this angle is alpha, and this angle is beta. Let me use some of the color. So this angle is alpha, the full angle, and the other angle is beta. This angle is beta. So what is theta 1? Theta 1 is equal to alpha minus beta. Now we have found the values of theta 2, plus I know what is xy. The link lengths are L1. So we know the link length is L2 and L1. So that's L2 and this is L1. Okay. So this is L2 and this is L1. Okay. So now from this figure, it's very clear that what is tan of alpha? Tan of alpha is equal to y by x. Okay, because you know the value of x and y, which is given. For inverse kinematics, we have been given x and y, the numerical values. So tan alpha is this. What is tan beta? Tan beta is equal to this distance, which is equal to L2 sine theta 2 divided by this full length, which is L1 plus L2 cos theta 2. So this is L1, that is L2 cos theta 2. That is tan beta. Okay. Now what is tan of alpha minus beta? So tan of theta 1 is equal to alpha minus beta, which is equal to this is equal to tan alpha minus tan beta. So this is tan Okay. So what we see is that we have found what is tan alpha. So if I take theta 1 is equal to tan inverse of this, so this will come there. Okay. So this is how we get the inverse kinematic solution for theta 1 and theta 2 using geometry for this manipulator system. Okay, so what will come in the bracket is tan alpha minus tan beta divided by 1 plus tan alpha tan beta. Okay, so this is what we saw in terms of how to do the inverse kinematic solution. So for the inverse kinematics, we see that first we write the forward kinematics equation, that is this one, this and this are the two forward kinematics equations. And in the inverse kinematics, given xy, you're supposed to find what is theta 1 and theta 2. Okay, now let's look at a numerical problem so that this concept of forward and inverse kinematics becomes a little bit simpler and easier to understand. And also we look at some things like numerical rounding of errors that can come in a robotic system. So let's look at this same problem. Now we have this manipulator system where this is my length L1, L2, let us say this is my x0, this is my y0, and z0 is coming out of the plane. This is angle theta 1, this is angle theta 2, and that is angle theta 3. Okay, so now suppose we have we are given that the position and orientation of this point is my xy, this is frame number 3, right? So this is frame number 3 or joint number 3. Now if I write the forward kinematics equation, then what we get is x is equal to L1 cos 1 plus L2 cos 1 2, and y is equal to L1 sin 1 plus L2 sin 1 2. Okay, these are two equations, and the third one is phi, the total angle is equal to theta 1 plus theta 2 plus theta 3. Okay, so now let's look at the forward kinematics problem. Let's look at the forward kinematics. I'm writing it as Fk. Now given L1 is equal to L2 is equal to 1 unit, and theta 1 is equal to 30 degrees, and let's say theta 2 is also 30 degrees, and theta 3 is equal to 30 degrees, just for example. Okay, now find xy. What is xy? So this is a very simple forward kinematics problem where I simply take the values that are given. X is equal to L1, L2 is 1, so cos 30 plus cos 30 plus 30, that is 60, 30 plus 30, which is 60, is equal to 1.3. You can use your calculator to find these numbers, 1.366. Okay, then what is y? Y is equal to sin 30 plus sin 30 plus 30 is equal to 1.366 again. So we get the coordinates of x and y. So the two coordinates of x and y are given by this is equal to x and that is equal to y. Okay, this is my forward kinematics problem. Now suppose I want to do the inverse kinematics now. Now in the inverse kinematics I am giving this number and this number. In x and y coordinates I will give as 1.36 and 1.3666. Okay, now L1, L2 equal to 1, just for simplicity. It can be anything actually. We are required to find what is the inverse kinematic solution. Okay, so let me again write the inverse kinematics problem. So inverse kinematics problem. So the inverse kinematics problem is given as, or stated as, given xy is equal to 1.366, 1.366, 1.366. Okay, find L1 and L2 are given. So L1 is equal to L2 is equal to 1 unit. Just for simplicity, find theta 1, theta 2 and theta 3. Okay, in the previous case we are given theta 3 is equal to 30. So what is phi equal to? Phi is equal to theta 1 plus theta 2 plus theta 3, which is equal to 90 degrees. Okay, so I can get phi. There is the total angle that the x3, this is my x3, this is x2 as per dh, and that is x1. So the total angle that x3 is making with respect to x0, so x3 with respect to x0 is given by the total angle which is given here, which is 90 degrees. Okay, now let me say that theta 3, find theta 1, theta 2 and theta 3 given xy is equal to this and phi, the angle phi is equal to 90 degrees. So I should get exactly the same answer if you understand what I'm trying to do. So this time I'm giving this as an input and I want you to find what is theta 1, theta 2 and theta 3 using inverse kinematics or IK. Okay, so how do we proceed? Let's draw the manipulator system again. So this was the manipulator system. Okay, so this is my L1, L2. No, sorry, there was another linkage here. Okay, so this is my theta 1, that's my theta 2, that's my theta 3, and this is my x1, x2. Let me draw it again. So this is the manipulator system. Okay, so this is my L1, L2 and L3. So this is x naught, that is y naught. And this is the point xy now. Okay, so now let's proceed. So as we have solved some time back, I will just refer to this, please refer to what we had just solved. So we found theta 2 is equal to cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2, this one. And then from there we convert to sine, then we convert to a tan, and then we get theta 2. Okay, so I'll simply use the formula. Okay, please refer back. So cos 2 is equal to x squared plus y squared is equal to x squared 1.366 squared plus 1.366 squared, x squared plus y squared minus L1 squared, 1 squared minus 1 squared divided by 2 into 1 into 1. So if you compute this, what we'll be getting is 0.8659. Okay, now from here we have to compute what is sine 2. Sine 2 is equal to root over 1 minus cos 2 squared. Okay, minus cos 2 squared, which is cos 2 squared, which is equal to root over 1 minus 0.8659 squared. So what we get is equal to 0.500. Now we find tan. So tan is equal to what? Tan is equal to tan theta 2 is equal to sine by cos, which is 0.500 divided by 0.8659. So this comes out to become equal to 0.577. So if I take tan inverse of this, so taking tan, so theta 2 is equal to tan inverse of 0.577, which comes out to be equal to 29.98. So please note this. It should have been 30 because we put exactly the same numbers I got here. Okay, but what you understand is that because we are using sine and cos, there will be other terms here. So whatever you do, it will not be exact. Okay, because we have taken only till 3 decimal places. You can take 4 or 5 decimal places, but still then what will happen, you will not get exactly 30 back because there is some error of the rounding of error because of sine and cos. Okay, so this is my theta 2. Now I need to find what is theta 1. So how do you find theta 1? So I'll just draw it very quickly. So this is, so how we find theta 1 is, so this is my L1, L2, and this is my theta 2. So we make this very simple construction that we make this very simple construction, and we say that this angle is equal to alpha and the other angle is equal to beta. So this angle is now my beta. Okay, and this is, sorry, I wrote a theta 2. This should be theta 1, and this is theta 1, that is theta 2. So theta 2 is known. Theta 2, we have already obtained theta 2. So theta 2 has been obtained as 29 point, theta 2 has been obtained as 29, theta 2 is obtained as 29.98, 29.98. Okay, now we need to find what is theta 1. Theta 1 is equal to, we know that first we have to find tan alpha. So tan alpha is equal to 1366 y by x, so 1.366, which is equal to 1. So tan alpha is y by x, right? Tan beta is equal to L2, that is 1 into sine 29.98 divided by 1 plus cos 29.98. Okay, so when we compute it, what we get is tan beta is equal to 0.2677. Okay, and then we get tan alpha minus beta, which is equal to tan alpha minus tan beta, 1 plus tan alpha tan beta, so it is 1 minus 0.2677, and here it is 1 plus tan alpha tan beta, so 1 into 0.2677, and this comes out to become equal to, this becomes equal to 0.5776. Okay, so this is what we get as now. So theta 1 is equal to tan inverse of 0.5776, which is equal to 30.01. Again, we see we don't get an exact value, but we get this value. So now we see that we have got theta 1, theta 2, and what were we given? Theta 3, phi was equal to inverse kinematics, right? Yeah. So theta 1, theta 2, I found theta 1, I found theta 2, I need theta 3. Now phi is given as 90. Okay. So phi is given, and phi is equal to theta 1 plus theta 1 plus theta 2 plus theta 3. Okay. So theta 3 is equal to phi, which was 90, minus theta 1, which is equal to 30.09 minus 29.98. Okay. So whatever is the answer, that is the value, 29.98, right? So what will be the answer? So this is equal to 90 minus 30.09 minus 29.98 is equal to 29.93. That is theta 3. Now, something very, very important to note here is that you did not get exact answers. You will not get exact answer because of the very simple fact that because we are using sine and cos, there will be some rounding off, and this rounding off will cause errors. Well, it's not errors, it's just rounding off. So it will not be exact. And this numerical problem comes in the problem of inverse kinematics. So in the next class, okay, so what we saw today is that there is this rounding off which happens, and because of rounding off, you will not get exact answers. So this is something that happens in inverse kinematics, and this is something you have to be a little careful of. Okay, because which also means that the controller will not get an exact answer. Okay, it will be a rounded off answer, which will be very close. So it will not be 30, it can be 30.005, or it can be 29.98, because the sine and cos terms are there. Okay, so today we looked at forward kinematics and inverse kinematics of a simple 2 degree of freedom manipulator. And in the next class, we'll look at the inverse kinematics of the Puma manipulator, which is 6 degrees of freedom. And we'll see that how we can solve the systematic way of solving for 6 degree of freedom. Then we'll proceed to the next topic, which is singularities and Jacobians. Okay, we'll stop here. Thank you.